Okay, so let's start from where we left over last lecture. So we implemented a backward Euler scheme that should be able to enable us to take much larger time steps, right? But last time I set delta t to 1 and the Newton's iteration didn't work. As you can see, the residual never converges. It decreases but oscillates around the order 1. So Newton's method doesn't always converge. You always need a close enough initial guess. And in this case, my delta t is too large. So if I take, for example, the delta t to 0.05, then when I run this, it converges very nicely, right? So you can see that the residual started with 1, it goes to 0.2, 0.06, 0.01, and then very quickly goes to 10 to the minus 3, 10 to the minus 6, and 10 to the minus 11 and 14. So whenever you see something like 10 to the minus 14, it converged to the point where further iteration doesn't really help you anymore. Why is that? That's the precision in which computers are representing numbers, right? So computers are representing numbers with a double precision 64-bit. And once you see order of magnitude about 10 to the minus 14, that's kind of on the round of error level of a computer double precision floating point. So we are pretty much converged in a few iterations, okay? And it turns out that the van der Pol oscillator is quite interesting if we take it to t divided by delta t, and if we run it like that, okay, we're gonna get a solution. Oh, shouldn't output this all the time. Let me just put a comma after this. So okay, so when we run it, it'll complete. And if I plot the same thing as I plotted before, so from 1 to t over delta t, so that's an array, times dt, actually from 0, and u. So if I plot this, I will still have a lot of things that I can see are not exactly smooth. So these are the locations where the Newton's method doesn't converge. All right, so I really need an adaptive method. So this is starting to get into what a mature ODE solver actually does, like ODE45, ODE23S in MATLAB. You actually have to detect if your iteration converges or not. If not, you have to cut the delta t. Okay, so here, what that means is that you can see we have a time loop in the outside. And within the time loop, we have a Newton's method loop, right? So loop within a loop. Now we're adding a third loop. The third loop is to loop over different delta t's until my Newton's method converges. All right, so let's wrap it over here. Okay, so for I try, let's try it 4 times. Okay. And I have Newton's loop like that. So instead of having a fixed delta t, I'm going to set t equal to 0. Okay, in the beginning, actually let me set t as an array, so starting with 0. And instead of looping over a finite interval, I'm going to say while t end less than my big T. Okay, so basically until I reach the end of my time integration interval, I'm gonna keep iterating. Okay, and not only when I have u equal to u and u next, I have t and t end plus delta t. Okay, this is because my delta t now actually changes depending on if my Newton's method is going to converge or not. Okay, so here, not only I want to detect if the Newton's method converges, if not, I'm going to cut my delta t. I would also need to increase my delta t back if my Newton's method converges really quickly, right? So what I'm gonna do is, if the norm of my residual is small enough, let's say 10 to the minus 9, I'm going to break. And then break means I'm going to exit the Newton's method loop. And then afterwards, I'm going to do a few detection jobs. So first of all, I'm going to, wait, let me actually put it over here in the beginning. As soon as we compute the residual, we can break, right? We don't have to do all the updates later. So first of all, I'm going to detect if I have converged or not. If I converged, I am going to exit the trying loop. All right. Okay. If not, I'm going to keep on the loop while saying delta t is cut by half. Delta t is divided by 2. Now, here, if I have converged, I am also going to say to detect if I Newton is less or equal, say less than 4. So if I converge really fast, okay, then I'm going to double my delta t before I exit. All right, does that make sense?
So you're only doing 4 steps on the dish?
I'm doing 12 steps in total, and but if I detect the residual converged early, I'm going to break out the loop, which means my I Newton when I break out the loop is going to be potentially less than 12. And in this case, I'm detecting if it's less than even 4, which means I will converge really fast, then it's a good opportunity for me to increase my delta t. Right? Okay. Make sense?